like to start out with a simple engineering physics problem. How can I take these 8 blocks size 4 centimeters by 20 centimeters and stack them in a way that the top block is completely separated from the bottom block? Most people would try this method. Unfortunately, it is less than effective. The correct idea depends on the theory of center of mass. The first block has a center of mass here, halfway down the block. This is the farthest over the previous block can be without the top one falling off. We can then repeat this process for the rest of the blocks. However, the center of mass is not always as easy to find as the first one is. For the next block, the previous 2 centers of masses must be averaged, and that is where the next block goes. This ends up being about 5 centimeters past the first edge, or 15 centimeters total. For each new block, a weighted average of the previous blocks will determine the new center of mass. When simplified, that formula looks like this. Each block is added following the sum from 1 to n of 1 over x, and voila! With 8 blocks, the displacement is clearly more than the 20 centimeters we needed. If 1 over x is graphed, it looks like this, and these points correspond to the various additions we made. If rectangles are drawn on top of these points with a base of 1, then the total area of those rectangles roughly represents the total distance traveled by the whole system. This is called a left-hand Riemann sum. The left-hand Riemann sum of 1 over x looks like this when drawn out. However, it's missing something. Our equation here, the sum from 1 to n of 1 over x, has one more term on the end. We can therefore say that the Riemann sum is less than a full distance. Also, looking at the graph, we can see that the total area of the Riemann sum is greater than the total area under the graph. Thanks to differential calculus, the area under this graph is represented by the natural log of x. Therefore, the Riemann sum is greater than the natural log of x, but less than our equation. This means that we can take out the middleman and just say that our equation is greater than the natural log of x. Now, if we change our Riemann sum to a right-hand approximation by moving the tops of the rectangles down like this, the total area is now clearly less than the natural log of x. Also, when we compare the new Riemann sum with our equation, the Riemann sum is simply our equation minus the first term, this one. So, with a little rearranging, we get that our equation is less than the natural log of x plus 1. By combining this with our other finding, we discovered that our equation, a very difficult one to determine with any accuracy, can be roughly approximated by the natural log of x and will always be within 1 unit. This allows us not only to see how far a certain number of blocks will reach, but to see how many blocks are needed to get a certain distance. Let's reuse the blocks from earlier and try to go a mere 2.5 meters. That ends up needing a whopping 974 million blocks. And if each is the predetermined 4 centimeters high, it ends up being 38 million meters tall, which is larger than the distance between the Earth and the Moon.